In this video, we're going to talk about stress transformation. Also, this video is going to help you to solve some questions under stress transformation, represent some stresses on sketch diagrams, and also generate some equations and understand some equations used in solving stress transformation. So this is a rotated element, and on this rotated element, we have various stresses acting on them. And these various stresses will help us to find or generate some equations solved under this data element. So the first we are going to look at is the stress in the y direction. So we'll be finding the stress in the y direction acting on this rotated element, and it's represented by stress in the y direction. And with the stress in the y direction, this could be negative or positive, depending on the direction. So when you come to the rotated element, where can we get this parameter? It's here. And I told you that this could be negative or positive, depending on the direction. So this arrow, when the arrow is going up, it means it's moving in the what? The y positive direction. And when it is moving down, it's moving in the what? Y negative direction. Next one we're going to talk about is the stresses in the x direction, which also could be negative or positive. And on this rotated element, we have it here. And depending on the direction, and here we could know that this is positive because it's moving in the x positive x direction. So if this is supposed to be like this, then our x, the stress in the x direction will be negative. Let's move on to the next equation, which can be generated from. We have another one which is called the shear stress in the x and y direction, and where that is always either this side in here, this side. So in that case we have that, and always it's negative. So when the value is given to you, that value. So I have this example here. This example, I have example 1, in which you are supposed to determine the stress on what x and y direction acting on these rotated elements, and also find the what the shear stress in the x and y direction. So for question number 1, let's find the x and y stresses. So with the x stress, we know that the x stress is not given to us. With the x stress is what? 0 megapascal. Let's note that if the x value is not given to us, it becomes 0 megapascal. Then we have our stress in the y direction to be what? 75 megapascal. And we have our shear stress in the x and y direction to be negative 55. This is for question number 1. And with question number 2, in this case, we have it like that. Our stress in the x direction is going to give us positive, right? It's going to give us positive 45 megapascal. Our stress in the y direction is also not given. So in that case, it becomes what? 0 megapascal. And then our shear stress in x and y direction, shear stress in x and y direction become what? Negative 25 megapascal. Let's move here with question number 3. Our stress in the x direction is going to give us it's moving in the negative direction, so we are going to have negative 46 megapascal. And with the stress in the y direction, we are going to have it to be positive 76 megapascal. And then our shear stress in the x and y direction, we're going to have it to be 26. So in this case, when the rotated element is given to you, for you to generate this, you can do it very easily. Let's continue. So let's continue with the next equation. And the next equation we're going to talk about is the plane principal stress. The plane principal stress, we have two, which is the plane principal stress 1 and plane principal stress 2. and all of them, they have their formula. Because we generating the plane principal stress was to generate another equation, find another term. So with that, we have it to be plane principal stress, that the formula is the stress in the x direction plus the stress in the y direction divided by 2 plus square root of the stress in the x direction minus the stress in the y direction all over all squared plus the shear stress in the x direction squared. This is for the plane principal stress 1, and for the plane principal stress 2, have it to be the stress in the x direction plus stress in the y direction divided by 2 plus square root of this is with the strain principal stress 2, we have minus this become minus half square root of stress in the x direction minus stress in the y direction all over 2 all square plus the shear stress in the x and y direction also square. So this is for the plane principal stress. We have two formulas for the first one, and let's take note of that. And then we move on to the next one I'm going to talk about is the maximum in plane stress. So for the maximum in plane shear stress, the symbol is as tau maximum. And in that case, with that formula, we are going to have it to be plus or minus the square root of the stress in the x direction plus stress in the y direction all over, then plus the shear stress in the x and y direction all squared. So this is the formula also for finding the maximum in plane shear stress. Now let's move on to the next equation. For the next equation, you're going to have something called the average normal stress. And with the average normal stress, we have it to be stress average, which is equal to the x and y stresses summation divided by 2. Then we move on to the principal angle. Principal stress angle, and with that is denoted by this. And in that case, for the formula generated, we'll have it to be tan 2 times the principal stress angle is equal to the shear stress in the x and y direction all over bracket open the x as the stress in the x direction minus the stress in the y direction divided by 2. And the last one we're going to talk about is something very important and we should take note of, which is called the absolute maximum shear stress at a given point. Its symbol is tau ASB. And for this, we consider two things. That is, we use the principal stresses to find the absolute maximum. That is the condition on that. So we use the principal stresses. So for the first condition, if the principal stresses, which is P1 stress P2, are all positive, it means that the value that you get are all positive. Then for you to find the absolute maximum shear stress, we're going to have the absolute maximum shear stress, which is this. We're going to have it to be the absolute value of stress 1 all over 2. So there's it. When the first condition is that when the principal stresses, which is P1 and P2, are all positive, for you to find the absolute maximum shear stress, we have it that to be the what? The principal shear stress of that's P1 absolute all over 2. The second condition is that if they are all negative, the principal stresses that you find are all negative. You had these answers all negative. If they are all negative, then the formula you're going to use in this case is that you're going to take the absolute to be the absolute of what? The principal stress 2. That's what you're going to do. And the third condition, and the third and the final condition is that when the principal stress 1 is positive, and then principal stress 2 is negative, for you to find the absolute maximum shear stress, you're going to have it to be that you're going to have the stress 1 minus the stress 2 all over 2. And this is the condition. These are the conditions you should know when finding the absolute maximum shear stress negative. So let's look at the presentation of stresses in an appropriate sketch. So as you can see, for the purpose of understanding, what you must know here, the key thing for us to draw this sketch is the principal angle, which is in this case this one. It's very important when solving this, so you must take very careful when solving this. If you get this to be positive, it gives you a different sketch, and if it's negative, it gives you a different sketch. So let's look at something here. For this, for the diagram represented here, it's showing us that this is positive. That is, the principal angle is positive. When the principal angle is positive, then it's established that the angle is going to move in a counterclockwise. So as you can see, it's moving in a counterclockwise. And then for you to draw the wedge element, now note that when representing the stresses in the sketch, we have two ways, which is two square stress element and what? A single wedge shaped element. But with this, I'm using a single wedge shaped element, in which we have this. This is the rotated element, and this is what we generate as the single wedge element, and this is the angle, which is the principal angle. And note that if it's positive, it has its own drawing, and if it's negative, it has its own drawing. So let's look at when it is positive. When it is positive, then we establish that it's going to move in a counterclockwise. So this will be the angle, positive angle, and then you draw your wedge element like this, goes up like that. And then you have your triangle with 45 degrees triangle. We have 45 degrees triangle. Then the values that you found for the normal stress average, you have the principal stresses and the shear stress. That's the maximum shear stress, you included there in that. Now note that these arrows or the signs are, you cannot just do it anyhow, right? Now note that when it is positive, the wedge element will come up, and when it is negative, we are talking about the principal angle. When it is negative, the wedge element is going to come down and move in the what? Clockwise direction. In that case, you draw your what? Your triangle. Very nice here. And then you have your 45 degrees. You have your tau max. You have your principal what? Stresses, and you have your normal stress average. That's the average normal stress. Yeah. But note that, as I said, we don't just draw this wedge element. So I'm going to teach you how you draw the wedge element. Now, these wedge elements are drawn using the principal values, which is principal value 1 and principal value 2. So with the principal values, whether it's positive or negative or something like that, which will help you generate the wedge element. But I've first established that when the principal angle is up, when it's positive, the wedge element is up, and when it's negative, the wedge element is. But then, how are you supposed to draw the wedge element? That's different here. So with one condition, when the first condition I'm going to talk about is that when the principal stresses, which is P1 and P2, are all positive, so positive, both of them are positive, the wedge element here, how we are going to draw it, that you are going to have your triangle, very nice, and you have your 45 degrees here, always compulsory. Then what you are going to do now is, let's see how we are going to put our values there. So we have both to be positive, so that means that we have, as you can see, this side is for the principal stress 1, so principal stress 1 is positive and it's moving this way, so principal stress 1, since it's positive, it should move in this way because it's moving in the positive direction. And we have our principal stress 2 to be also positive. We have it to be positive, positive. So all are positive. Now, you see the direction of the tile marks. How is the direction going to be? Note that if all are positive, the tile marks will move up like this. This will be tile marks. And then the average normal stress, it depends. If the average normal stress is positive, then it goes up like this. But if it's negative, it comes down. So this is the first one. If both the principal stresses are positive, you will draw a wedge element like this. Either if they are all positive, you draw a wedge element and you look at the angle. If the angle is positive, that means that the wedge element is going up, and this will be the angle. And if it's negative, the wedge element is coming down, which is this. Now let's move on to number 2, the condition 2. With condition 2, let's look at if all are negative. So if the principal stresses are all negative, what are you going to do? All negative. So for you to draw the wedge element, if they are all negative, you're going to have it to be like this. Sorry for my sketch. And then we have, they are negative, so it's going to move in the counter direction. They are going inside. It's negative. This also will move. So we have our principal stress 1 and 2, they are negative. Then one will ask, how is the maximum shear stress going to be? If both are negative, then it's going to move down and the arrow will come down here, right? So if they are all negative, it's going to move down, the arrow will come here. Then we'll have our tau maximum to be here because they are all negative. And then depending on the direction of your average normal stress, if it's positive, it moves here. If it's negative. And the third condition I'm going to look at is if either one of them is negative or positive. So we are going to use this. If the principal stress 1 is positive and the principal stress 2 is negative, so the stress for the wedge element, the maximum shear stress will come down like that. So if they are all positive, know that it goes up. If they are all negative, it comes down. If one is negative and one is positive, it comes down. Let's take note of that. So in that case, let's take some example for us to solve and see how we're going to do it. So in this example, we are asked to determine the principal stresses and the maximum in plane shear stress acting at the point using this stated element. And also we should show these stresses in an appropriate sketch and determine the absolute maximum shear stress at the point. So in this case, what we need to do is that we have our rotated element and we should get some values from it because we have the x and y stresses and have the shear stress in x and y direction. So let's go. So first, from the given stresses, the values to be used in the stress transformation equation are, we have our this, which is the stress in the x direction. How do we, is it positive or negative? It's positive. We have positive 70 megapascal. Then we go to our stress in the y direction. The one is also positive 150 megapascal. Then we go to our shear stress in x and y direction. And that one is always negative 55 megapascal. So we need this information from this rotated element to continue to generate the stress transformation equation. So these are the 3 things we need, and 3 important things, because when you miss any of this, that means that your solution is wrong. So for first question, we asked to determine the what? The principal stress. So A, we are determining the principal stress and the maximum in-plane stress. We are finding 1, 2, and also we find our tau max. So let's solve for our principal stress 1. So for principal stress 1, the formula is going to give us, we have the stress in the x plus the stress in the y direction divided by 2. Then we have plus the square root of the stress in the x minus the stress in the y all over 2 squared plus we have our tau xy squared. In that case, we do substitution. In this case, we put in that we have 70 megapascal plus 150 megapascal divided by 2, then plus square root of 70 minus 150 divided by 2 all squared plus minus 55 squared. So in that case, when you do that correctly, you're going to have our principal stress 1 to be 178.0 megapascal. So let's solve for the 2. The principal stress 2, you're going to have that you're going to have this plus that all over 2. Only the positive sign will change to negative. Square root of stress x and stress y divided by 2 all squared, then plus the tau xyz squared. So in that case, when you do your substitution inside, or substitution, you're going to get 70 plus 150 divided by 2 and minus square root of 70 minus 150 divided by 2 all squared plus minus 50 squared. And when you do that correctly, you're going to have your value to be 42.0 megapascal. Very simple as that. This is just substitution with the formula. So it's important to know the formulas. Then we move on to the tau max, which is the tau max. For the tau max, what you're going to do is that the formula for the tau max is the maximum in-plane shear stress, which is the tau max. In this case, you're going to have plus or minus square root of the stress in the x direction minus the stress in the y direction all over 2 all squared, then plus the tau xy squared. In that case, when you do that correctly, you are going to have that plus or minus square root of 70 minus 150 all over 2 all squared, then plus negative 55 squared. And then our maximum shear stress will be plus or minus 68.0 megapascal. Then we also need to find something very important which will help us to draw the wedge element. And in this case, with that one, is termed as the normal, that's the average normal stress. So for the average normal stress, we find the average normal stress, and we find the average normal stress, we are going to get 70 plus 150 divided by 2. In that case, our answer will be 110 megapascal. So we now know the value for the principal stresses, which is principal stress 1 and principal stress 2. So principal stress 1 was 178.0 megapascal. Principal stress 2 was 42.0 megapascal. We have our maximum shear stress to be 68 plus or minus 68 megapascal, and we have our average. This is very important. We have the average normal stress to be what? 110 megapascal. And for B, we are supposed to what? Let's do B. We are supposed to show these stresses in what? Appropriate sketch. So from what I explained, for us to show the appropriate sketch, what you need to know is that we need some very important information, which in this case, we need a principal angle, right? And for us to find the principal angle, we know that, so let's solve for B. For principal angle, we know that tan 2 theta p is equal to what? The shear stress in the x and y direction, bracket open, the stress in the x minus the stress in the y divided by 2. And in that case, when you are doing it, you are going to have that our angle, which is the going to have tan 2 theta p is equal to negative 55 megapascal all over 70 minus 150 all over 2. In that case, when you find our theta, it's going to be simplified to negative 55 megapascal all over negative 40 megapascal. So this will cancel this will cancel this. So when you find the tan inverse and divide by 2, you're going to know that our theta p is going to give you 27.0 degrees. And what does this tells you? Because it's positive, the wedge element will move up, and then you know that, and our theta p will be equal to 27.0 degrees. And what does it tell you? Because it's positive, our wedge element is going to move up. Let's take note of that. And also, before we draw the wedge element, we need to know the values for the principal. Was the principal stress that we had, are they opposite or negatives? And we know how we draw it. So then let's draw our wedge element. So for our wedge sketch, we have, first you need to draw your normal one. This is the one question given to us, so you draw your question first. This is the question. This one there is very easy to sketch because the question has been given to you already. Have this one going down from the question. You have this one coming down like this, and we have this coming here. We have our arrow moving here. We have one arrow so coming here like this, and we have one arrow so moving up, and this x value also is moving up. So here we have it to be what? The y value was 150 megapascal. The x value was 70 megapascal. We have our shear stress in the x and y direction to be 55 megapascal. So then let's try and generate our wedge element. So for our wedge element, that's the drawing. We will first draw a line like this, and then our angle generated was 27 degrees. So let's draw it up. We have our angle here, which is moving in the counterclockwise to be 27. So this is 27 degrees, right? Yeah, because it's positive, it's moving up. Then our wedge element, we have our triangle here. Let's draw a triangle. In this case, this side is what? 45 degrees. Now we are going to now add our various parameters. So now let's see. For our solution, we had that the principal stresses, they are all positive, right? For the principal stress that we had the principal stress 1 to 178 megapascal, and the second one is 42 megapascal. So they are all positive. So let's indicate, since they are all positive, the arrow will move here and this side will move here. This is 2 and this is principal stress 1, right? So then principal stress 2 was 42 megapascal, and principal stress 1 was 178 megapascal, and they are all moving in the positive direction, right? Then if they are all moving in the positive direction, where will the direction of the that's the stress, which is the maximum in plane shear stress, move? It's going to move up like this, and then it will be like this, right? Then we have it to be that one. We had it to be 68 megapascal, 68 megapascal. And then what was our average? The average that we had was 110, and that one is in tension because it's positive. So it's moved this way. Its intention is add it to be 110 megapascal. So this is how we draw the wedge element for this question. Very simple as that. The key thing is for the principal or stresses, also the angle that you get, whether positive or negative. Now let's look at second question, which in C, this is B. So with C, they are asking us to what? Compute our absolute maximum, right? That is question number C, absolute maximum. And for the absolute maximum, that is tau ASB, we will use the principal stresses. And for the principal stresses, we notice that they are all what? They were all what? Positive. They were all positive. And if they are all positive, it means that we're going to have the principal stress 1, that's P1 divided by 2. And then we have it to be 178 megapascal divided by 2, which give us 89.0 megapascal. Very simple as that, because the principal stresses are all positive, and then we do it that way. Let's move on to the next question. So in this question, we are asked to determine the principal stresses, the maximum shear stress acting at the point, show these stresses on an appropriate sketch, compute the absolute shear stress at the point. So we have this. So first, we need to generate our given stress value. So first, we have the stress, the y direction and x direction. So x direction, we could know that it's moving to this side, so it's going to have negative 62 megapascal. You can pause this video and do the y direction and the tau xyz. For the stress in the y direction, you know that it's also negative, right? Because it's moving in the negative direction, negative 94 megapascal. And then we have our xy to be tau xy to be negative 42 megapascal. So from this, we're going to solve our value. Now from this, we know that we determine the principal stresses. We know that for A, principal stress 1 is going to give you what? As the formula goes, that we're going to have x direction plus y direction divided by 2 plus the square root of x direction minus y direction divided by 2 all squared plus tau xy squared. So in that case, when you do substitution inside, you're going to have it to be negative 62 minus as plus minus 94 all over 2, then plus the square root of negative 62 minus, as this in bracket, minus negative 94 also in bracket, then this all over 2, this is a big bracket, squared. Note that their units are in megapascal plus the minus 42 all squared. So when you do that correctly, the principal shear stress, first one will give you negative 31.1 megapascal. So the first principal stress you had was negative 33.1 megapascal. Let's solve for the second one, which is second one. In that case, we're going to get in the x direction plus y direction divided by 2 minus the square root of this minus this all over 2 squared, then plus the tau xy squared. So then we do substitution, negative 62 plus minus 94 megapascal divided by 2 minus the square root of negative 62 minus negative 94 all squared, this divided by 2, then plus our negative 42 all squared. In that case, when you do that correctly, you're also going to have it to be negative 122.9 megapascal. So then the next we are supposed to find is find our so in this case you also finding the maximum in plane shear stress. So the maximum in plane shear stress, which is tau max, you know that with that the formula that you're going to have is going to give you plus or minus the square root of plus or minus the square root of the shear stress minus this all over 2 all squared, then plus the xyz squared. So in that case, when you do the substitution very correctly, you're going to have it to be 44.9 megapascal by doing your substitution. Then we need to find the average normal stress, which is the average avg average normal stress. And for the average normal stress, you know that we're just going to add this plus that divided by 2, and in that case, when you do that correctly, you're going to have it to be 78.0 megapascal. And in this space in what compression, since you're going to get the negative value, which is negative 62 minus 94 divided by 2, and the answer you're going to get is a negative value, and it's in what a compression form. So it's in a compression, so this will help you to, when drawing your wedge element, you shouldn't forget that. Now let's move on to finding the angle. So we knew that our P1 was so from what you've solved, you know that our principal stresses were this. Our maximum in shear force, that's the shear stress, was 44 megapascal, and the average that we had was, that's an average normal stress, was negative 78.0 megapascal. For you to write it in a positive way, it means that's 78.0, and it is in what compression. Now we should find the angle, that's the principal angle, which you know that this is for B. We drawing the wedge element, we should find the angle, and finding the angle, we need to know that theta 2, that's tan 2 theta p, that's the principal, equal to the tau yz all over x minus x1 y. Then we had it to be negative 42 megapascal all over bracket open. We have it to be negative 62 plus 94 divided by 2. And in that case, when you find our theta, because you divide it by 2, and our theta going to be negative 34.6 degrees. So our theta is in what, negative 34.6. What does it tell you? It means that the angle will move in the clockwise direction. So drawing our wedge element, let's draw our wedge element. So we have our force. This is our normal drawing, which was given to us. Put here, which this one was given. Had this. This was moving in this direction. We had this moving in this direction. There's a normal one. The question given to us. So you draw the question first, and then we knew that our value was moving here, which and this one was coming. And this was 62 megapascal. And please don't forget to bring the unit. And this is 94 megapascal. Shear stress was what? 42 megapascal. Now drawing our wedge element, we need to draw this, include our line like this. And then the angle we had was negative. That means that the wedge element will go move down because the angle we had was negative. And it will move in the clockwise direction. And this was 34.6. Then let's come to our wedge element. So you draw your triangle very nicely. This 45, right? Okay. So after drawing our triangle, let's look at the condition. So we had both our principal stresses to be what? Negative. That means that the principal stresses it will be going inside, right? The arrow will be going inside. This one too, the arrow will be going. What was our average? Average to it was in compression, so the average to the average arrow will be going inside because also in compression. And since they are all negative, the tau max also will move down, as I told you to move down. So this will be tau max. Very simple as that. And then we put our value so that we have this to be 78 megapascal. We had this to be 33.1 megapascal. We had this to be 122.4 megapascal. And we have our maximum 49. This is how we can represent our wedge. Simple. Let's solve the last question, which is the absolute shear force. For the absolute maximum shear force, we established that that is T, the absolute maximum shear force. Now we're going to use the principal stresses, and we realize that our principal stresses, all of them were negative. And if all of them are negative, this formula is what we are going to use. This is P2 divided by the 2, right? Find the absolute of that. And that in that case, you're going to have it to be the absolute value of 122.94 megapascal divided by what? 2. And the absolute value of the negative number is what? Positive. So you're going to get 61.5 mega. Thank you very much for watching this. Hope you